the effective stress calculation we have talked about is for static case, meaning there is no flow of water through the soil mass. If, however, the water is seeping through the soil, the effective stress will change, will be different from the one for static case. Depending on the direction of the seepage, effective stress may increase or decrease. So shown on this slide is a case of upward seepage. Water is basically seeping through the soil in the upward direction. So that's your soil sample. For this case, if you look at any point, say point C in the soil sample, the effective stress at point C actually decreases due to the that upward seepage. On this slide is a case of downward seepage, so water is flowing downward through the soil mass. Again, if you look at this point C inside the soil mass, the effective stress at point C will increase due to this downward seepage. To understand why seepage changes effective stress, so I'm going to show the total stress, pore pressure, and effective stress of a particular point C in the soil mass where water is seeping through. So we have this point C here. So start with the upward case. So for this upward case, we have water of height h1 above the soil sample. So this is your soil sample. And this is water. And the water is seeping in the upward direction. For point C, it's at a distance z from the top of the soil sample. So the total stress at point C, sigma c, equals to h1, that's the depth of that water body, times gamma water, plus z times the unit weight of soil, let's say it's gamma saturated. So this is saturated unit weight of soil, and this is water. And then the pore pressure at point C, U sub C. Okay. So for pore pressure at C, we have a standpipe here. So this is the standpipe. So the pore pressure at C is basically this height of water inside the standpipe times the unit weight of water. So this height has several parts here. So first part is this top portion here, which is small h over h2 times z. Okay, that's this portion here. And then we have the second part, which is simply h1. And finally, this is z here. Okay. So the pore pressure at point C is, let's say, h1 or z plus h1 plus h over h2 times z. So that's the height of water inside that standpipe at C. Then multiply that by the unit weight of water, you get the pore pressure at C. And finally, by effective stress equation, sigma C prime, that's your effective stress at point C, is total stress minus pore pressure. So if you substitute the total stress and pore pressure expression into this, we're going to get Z gamma saturated minus gamma water minus Z times H over H2 gamma water. So this term, this difference here, is by definition is the buoyant unit weight, gamma B, or sometimes we use gamma prime. So this is buoyant unit weight. And this ratio here, small h over h2, this is hydraulic gradient I. This is hydraulic gradient. So then your effective stress sigma c is simply z times the buoyant unit weight gamma prime minus z times I gamma water. So that's your effective stress with upward seepage. And you can see the first part here, so this is effective stress for static case. So if you don't have any seepage, the effective stress at C is simply Z times gamma prime. And this portion here, this is due to upward seepage. Okay. So you can tell from this expression, the sigma C prime with seepage is smaller than the sigma C prime for static case. Now for the downward seepage case, again, we're going to look at point C in the soil mass. So this point here. So for downward seepage, first the total stress sigma C stays the same. So sigma C equals to H1 gamma water plus Z times gamma saturated. And then the pore water pressure at C for downward seepage case, UC, again is the height of the water level inside the standpipe. We have, this is at point C. So this height here is, if you look at this plot here, this portion here I highlighted, this is H1 plus Z. And then you have this small portion here. So that's this portion. This portion is H over H2 times Z. So the water level inside the standpipe at C is H1 plus Z minus H over H2 times Z. And then you multiply that by the unit weight of water to get pore pressure at C. And finally, similar as the upward case, the effective stress C prime is the difference between total stress sigma C minus pore pressure sigma C. And then if you substitute sigma C and UC into this effective stress equation, you're going to get Z times gamma saturated minus gamma water plus Z times H over H2 gamma water. Okay. Again, using buoyant unit weight, this is gamma prime, and this H over H2, again, that's your hydraulic gradient. So the effective stress of sigma C prime due to downward seepage equals to Z times gamma prime plus Z I gamma water. So this additional term here is due to the downward seepage. So the first part here, that's again for static case. We don't have any seepage. So from this expression, you can tell the effective stress sigma C prime is the its value for static case plus additional term due to seepage. So that's why you have a higher effective stress due to downward seepage. For both of these effective stress expressions with seepage, there's a common term. So that common term is the hydraulic gradient I times the unit weight of water. So this is called the seepage force per unit volume. So seepage force. Okay. Moreover, if we look at this effective stress equation with upward seepage, there's a critical condition when, so if the seepage is increasing such that the effective stress sigma C prime is 0 for the upward seepage. So if you have sigma prime equals to 0 for an upward seepage, so this critical condition is when soil loses its stability, and this is referred to as boiling or a quick condition. So for this case, the hydraulic gradient at zero effective stress is called ICR. So this is called the critical hydraulic gradient. Okay. So again, this is for zero effective stress. Okay. So this critical hydraulic gradient I sub CR can be solved by substituting sigma C equals to 0, Z times gamma prime minus Z I critical times gamma water. So then this critical hydraulic gradient for boiling or quick condition of soil equals to gamma prime over gamma water. Okay. So this gamma prime is the buoyant unit weight. Okay. So for most soils, this critical hydraulic gradient ICR is between 0.9 to 1.1. Now let's take a look at one example of stress calculation where there's an upward flow of water through the soil layer, the sand layer. So this is a soil layer, it's a sandy soil, and you have upward water flow. And so you're asked to calculate the total stress, pore pressure, and effective stress at point A and B, and also the seepage force per unit volume, which we have previously defined as hydraulic gradient times unit weight of water. So for this sand layer, we are given void ratio E 0.52 and specific gravity, which is GS of 2.67. So use the weight volume relationship, we can calculate gamma saturated, and for this problem, the saturated unit weight of the soil is 20.59. Okay, so let's start the total stress calculation, pore pressure and effective stress at point A. Let's look at point A first. So for point A, total stress sigma again is the total weight above point A per unit area. So this includes the weight of the water. So this is 0.7 meter of water. It's a 0.7 times unit weight of water plus, so A is 1 meter below the top of the soil layer. So it's 1 times gamma saturated. So if you plug in, substitute these numbers for unit weights, 0.7 times 9.81 for unit weight of water plus 1 meter times 20.59. This is 27.46 kilonewton per meter square. So that's the total stress at point A. Then for pore pressure, so we have previously shown the derivation of this pore pressure at any point inside this soil layer. So this pore pressure is 1, so that's at 1 meter plus 0.7, then plus, because of the upward seepage, you have this additional term, 1.5, which is the total head loss over 2, which is the total depth of this soil layer. So that's, by definition, is hydraulic gradient. Then times is distance water travels from entering into the soil to point A, which is 1 meter. Oops. And then times unit weight of water. So this gives you 2.45 times 9.81 equals 24.03 kilonewton meter square. So then the effective stress at point A, sigma A prime, is the difference between the total stress sigma A minus pore pressure UA, and this is 3.43 kilonewton per meter square. Okay. So that's point A. And then for point B, so point B, the total stress sigma B is 0.7 times gamma water plus the height of that soil layer times gamma saturated of soil. This is 0.7, 9.81 plus 2 times 20.59. Okay. So the total stress at point B is 48.05 kilonewton per meter square. The pore pressure at B, so UB. So from this figure, you can see there is a standpipe at point B. So the height here, that's the height of the water inside that standpipe. So it's 2 plus 0.7 plus 1.5. So then the pore pressure at B is simply the height of the water, 2 plus 0.7 plus 1.5 times the unit weight of water. So this gives us 4.2, 9.81. So the pore pressure at point B is 41.2 kilonewton per meter square. Finally, the effective stress at point B is sigma B minus UB, and this is 6.85 kilonewton per meter square. And for the seepage force per unit volume, by definition, this is part A. So the seepage force per unit volume by definition is the hydraulic gradient I times unit weight of water. And the hydraulic gradient I is the total head loss 1.5 divided by the total depth of the soil layer 2. So again, this is the total head loss, and this is the total distance. So that's your hydraulic reading times unit weight of water, 9.81, and that equals to 7.36 kilonewton per meter cube.